Okay, let's get started. So today we're going to continue our discussion about ridge regression and Lasso. Last time we got this far, and we saw that in ridge regression, you take RSS and you add onto it a penalty which tries to make the beta coefficients 0 or at least small. Lasso is similar. You start with RSS and you add a beta penalty. The difference is that in this case, the penalty is the sum of the squares of the beta coefficients, whereas in this case, it's the sum of the squares. Sum of absolute values versus sum of squares. So we saw a little bit of intuition here about maybe the difference between absolute value penalty and square penalty in terms of what happens near the origin and what happens farther from the origin. Okay, so these are the two methods. Let's start by discussing ridge regression. And like I mentioned in the announcements, I made a couple changes to the slides to try to clarify things a little bit. Okay, so as we just saw for ridge, the cost function is we start with the RSS, y minus ax squared. This is the Euclidean, sorry, not ax, x beta. Y minus x beta squared, and this is the Euclidean norm, plus alpha times beta squared, again, Euclidean norm. And so using the same techniques that we used back in Unit 2, where we derive the least squares equation, the equation for the least squares beta, you can also derive this equation without too much difficulty. I think, yeah, this will be a homework problem. So it's somewhat intuitive. So if alpha is 0, then we would just get least squares here. And now you can see if alpha is 0, that would be the least squares equation, right? The one we derived for beta least squares. So now when we have the alpha, what changes is we have this term here, alpha times the identity matrix. Okay, so this is what happens when you add this penalty. Okay, any questions on that? Okay, so I'm not going to get into the details of the derivation, but they're exactly the same as we did with the least squares case. So basically you set the partial derivatives with respect to each of the beta j's. You set them to 0, and you solve for the resulting betas. And after a little bit of effort, you get this. Okay, so the important thing is to understand the effect of this term. And I think the best way to understand it is by taking a look at what's called the coefficient path. The coefficient path is this plot on the right, and it shows the values of all those beta coefficients versus alpha as you change the penalty. Okay, so let's look at the extreme cases. In the extreme case that alpha is 0, we said we just have RSS, and so in that case, ridge would give us the same as least squares. And that is sort of shown by the left side of this plot where these alphas are small. Notice the alphas are on a log scale here from 10 to the minus 1 to the 10 power 4. So for very small alphas, the coefficient values that we get are the least squares ones. Right? Now let's look at the opposite extreme. What happens if alpha is very large, like here it's 10,000? So in that case, this term is so much bigger than this term that essentially this term is, it's so small it's as if it's not there. And in that case, we minimize this. And what is the minimum value of that? So this is just the sum of the beta squares, right? So what's the minimizing value? What betas minimize that? Zeros, exactly. And so that's what you see here. You see the coefficients, they're all going to 0 asymptotically as alpha goes to infinity. They're never exactly 0, but as alpha goes to infinity, in the limit, they become 0. Although you can see they're pretty close to 0 already here. Okay, so what's more interesting is what happens for the alphas in between that are not too small or too large. Here, interesting stuff is happening. In fact, some of the coefficients, like this brown one, starts out negative, eventually crosses the 0 axis and becomes positive before settling down again. So there is interesting stuff happening here. But is this going to be useful for feature selection? What do you think? Let me ask. Let's see. Is Srinivasan Subramanian here? Yeah. Okay. What do you think? Is this going to be a useful approach to do feature selection?
Depends.
What do we want when we do feature selection? What do we want to happen?
Minimum cost.
Not exactly. There's something more specific about the beta coefficients. Okay. Yeah.
See which ones are more related to one another.
Not exactly. Any other ideas?
How big the weight is.
There was something very specific we wanted to happen to the betas in feature selection.
Find the ones that are less important to the model.
Yeah, and how do we know whether they're less important based
A
on
low parameter.
So, okay, when the beta is 0, that means we're taking that feature out completely, right? So in feature selection, we want to set a subset of the weights, the betas, to 0, and that means the ones that are non-zero are the ones we're going to use. So if this was a good method, we would see some subset of the betas going to 0 and others being non-zero. Do we see that? We don't see that. We see essentially all of them are non-zero and eventually they all become 0. So this is not doing any sort of feature selection for us. So it's not useful for feature selection. Okay, that's a key point. Okay, any questions on that? All right, so now you might think, well, why did we even discuss this method? So it actually is a useful method. It's useful for something else. It's useful when the features are highly correlated, which is definitely something that can happen in practical data sets. So this is an explanation of what happens if you try to use standard least squares regression with highly correlated data. So here is the regular equation we have for the least squares parameters. And when you look at this part, what happens when features are highly correlated is that the eigenvalues of this matrix, a few of them get really small. And when you invert that matrix, those really small eigenvalues turn really giant, because it's like inverting a small number makes it giant, right? And then so that those giant numbers end up multiplying these and making these betas also giant. Then when you go to apply this beta vector to do your prediction, you find that these giant values are going to essentially make your prediction very sensitive to small changes in the x. Okay, so and any model that's very sensitive to things you don't want it to be sensitive to is basically an overfitting type of model. So this is another type of overfitting, a little different than the one we saw with the model being too complex in terms of having too many parameters. Here, it's just a highly sensitive model that's going to be sensitive to small changes in x which are not important. Okay, so this is a real issue in practice. And so what we do in ridge regression is we add this extra term, which basically is telling us you have to keep the betas small. You can't let them grow large, because the penalty that we saw over here says when these betas get large, the penalty becomes huge. So it just prevents that from happening. Okay, so I did a little experiment. This is a synthetic example. It's in now a demo 4B, different than the PSA demo, where I created a noisy linear model, the same one we're used to seeing, where there were two beta coefficients, just beta 1 and beta 2. And the targets were, so the true coefficients were 1 and -1, and the targets were basically corrupted with some Gaussian zero mean noise. There's just two features here. And this is what happens. This is the coefficient path for ridge. So the first thing to look at is what happens when the alpha is really small. We know that these are like the least squares parameters. And in fact, here are the least squares parameters. You can see their values are around -30. Remember the true values, these are the true ones, were 1 and -1. Okay, so the least squares ones are extremely far from the truth. And that happens because of this correlation that I described earlier. Now, we also know that in ridge regression, if you choose alpha too large, what happens is all your coefficients go to 0. And that's what's happening over here. So this is useless as well. But what's interesting is that for this middle range of alpha, ridge regression is actually getting very close to the true parameters. This is where it's working its magic. Okay, and so that's just a simple example that I constructed. It's synthetic, but this stuff like this does happen in practice, and you'll see an example of this actually in the lab for this unit, for lab 4. Okay, any questions so far on anything I've said here? Okay, so again, ridge regression, not useful for feature selection, but it is useful when your features are highly correlated. Now you might also ask, well, how do we choose alpha? So in this plot, it's a little bit unfair because I know the true ones here because I made the model. And so it's clear that alphas in this range are what we want to use. But in practice, you don't know the truth. Okay, so you can do cross-validation like we always do. So here I'm doing the cross-validation mean squared error. For this experiment, I used leave one out cross-validation because I didn't have that many samples. I could afford to do it. And here's the curve we get. And you can see that all these values of alpha give pretty low cross-validation MSEs. The absolutely lowest one turned out to be right here. And if you look at where does that correspond to over here, that's right here. So it ended up choosing some very good coefficients, very close to the truth. Okay. And here you can see the penalty. So even though these guys are extremely far from the truth, it turns out that what really matters mostly is the difference between them. And so even when you use this model, the performance is actually not terrible. This is like the cross-validated MSE, but it's certainly worse than this performance. So you do get a boost from using ridge regression in terms of your prediction error. Okay, so that's what I wanted to say about ridge regression. Any questions about ridge and why we use it? Okay, great. So now let's move on to Lasso. So Lasso is a little bit different. On the surface, it looks similar. So we have y minus x beta. It's the RSS part. But then we have our penalty, which uses the one norm, which is the sum of the absolute value of the beta coefficients. So in this case, we cannot derive a closed form expression. In fact, the whole approach we've been using fails here because we cannot even differentiate this because at the origin, the derivative doesn't exist. So if you try to just remember what this looks like over here, if you try to differentiate this red curve, there is no derivative at the origin, right? So we can't use that whole trick of setting the derivative to 0. Now, it turns out that this is what's called a convex loss, and we'll learn exactly what that means in Unit 6. But when it's convex, the optimization problem is tractable. It can be done. It can be done numerically. And there's various approaches you can use, but basically in scikit-learn, they have implemented several of those approaches in the Lasso method, so you guys don't have to be masters of that optimization. You just have to know how to use scikit-learn. And I think, again, the most insightful thing is to take a look at the coefficient path when we do this. So here again, we have alpha on the horizontal axis and the beta coefficients on the vertical axis. As before, when alpha is really small, it's as if it's not there, and you get things that are very close to the least squares values. On the other hand, when alpha is extremely large, it's as if this one is not there. And here again, the optimal thing to do is to set all the betas to 0. But in between, for alphas in between those extremes, interesting things happen. In particular, this is what happens. So these the beta coefficients, as alpha increases, they start shrinking. But what's interesting is, at some point, they go to exactly 0. So here, after this alpha, this brown one is exactly 0. Then after this value of alpha, both the brown and the pink are exactly 0. And then after this value of alpha, the red is exactly 0. So they just start turning off one by one. When you're in this range of alpha between here and here, there's only one coefficient left, and it's the blue one. This is LCA val, whatever that is. And so this model says, basically, or Lasso says, if you're going to just choose one and only one feature to use, it should be this one. If you want to choose 2 features to use, it should be the blue and the purple ones. If you want to choose 3 features to use, it should be blue, purple, and orange. Right? That's what you get. And you get those different choices by choosing alpha. The larger alpha gets, the fewer coefficients you have, but now you know, for any alpha, you know which subset you have. So it kind of gives you like a ranking of the features. Okay, so this is definitely useful for feature selection. It sets a subset exactly to 0 and tells you which ones are non-zero. Those are the ones you want to use.
If 2 features, like for example the orange and the purple there, have very similar alphas that they go to 0, does that mean they're correlated, or is that entirely unrelated?
I think it's unrelated to correlation. It means that according to Lasso, they are of similar value. They may be totally uncorrelated. Okay. Any other questions? Okay. So the aspect that's nice about Lasso is that the features turn off, and therefore we know we can discard them. What's not so convenient about Lasso is that the features that remain non-zero, or the coefficients that remain non-zero, they start shrinking towards the origin. And that's bad. We don't want that because the actual coefficients, the betas that Lasso gives us, the ones that minimize this cost, we want to look at which subset is non-zero, but we want to ignore the actual values. Okay, so that's essentially what we want to do. So this is what we said. How it's good. This is how it's bad. So essentially, you can say that these coefficient values are biased. They're systematically smaller than you would like. Don't want to use them. Okay. So yeah, Lasso can be used for feature selection. Okay, so what we do want to use, though, is we want to use the indices of those non-zero coefficients, like the J's that index the non-zero ones. So here, I'm writing that set of indices, the J's, such that, this colon means such that, the set of J such that beta J is not equal to 0. Those ones I'm storing as this script J Lasso. And now, those are the features I want to use. Xj, for which the little j is in the script J Lasso set. And we want to do standard linear regression with those Lasso selected features. So that's how we actually want to use Lasso. Okay, so I'm going to show you a whole bunch of scikit-learn code coming up that gets into all these details, and there are a lot of details, because what we want to do at the end of the day is a little bit tricky. We don't want to do cross-validation with Lasso alone. That's easy. We want to do cross-validation with the Lasso selected least squares features, or least squares coefficients. So we're using Lasso to tell us which coefficients to estimate and then use least squares to estimate those. That's what we want to do. So that's a little bit tricky. Okay, we don't want to use not the biased Lasso coefficients like B Lasso. Those, don't want to use them. Yeah, is this pretty clear what I'm saying here? Okay, yeah.
Lasso still doesn't help us with the number of features we want to use. Right?
So we have to choose alpha,
Yeah.
right? So we have this, yeah, the main tricky thing to do is how to select alpha. The larger alpha is, the fewer features will be left non-zero. Those are the features we'll be using. The fewer beta coefficients are left non-zero, and then the fewer features we'll be using. So that's sort of the tricky thing, is how to choose alpha. But when we choose alpha, we don't want to choose alpha based on these biased coefficients, but on how least squares would turn out if you use those three coefficients.
So like the ridge regression is, we could use it for model training. And,
So ridge regression, we said, is useful for highly correlated features, whereas Lasso is useful for feature selection.
yeah.
And sometimes you want to use both, because maybe you have highly correlated features and you want to use a subset of them. So you actually want to do both together.
Okay, so like, the lasso we can also use it for training. Like,
So all of these are methods that are used during training to compute our beta coefficients for linear regression. Yeah. I'll show you in detail how we're gonna use the beta coefficients and everything when we look at the code. It might answer some of your questions. Okay.
What if you don't know if your features are correlated?
Good question. So what you can do is you can try ridge regression, and you can vary the alpha, and if you see no cross-validation performance gain by using a large alpha, like if alpha equals 0 is the best, then you can conclude ridge doesn't seem to be helping me, probably don't have enough correlation to make it worthwhile. Okay. Other questions? Okay, yes.
Are you able to use ridge to determine then if values are correlated in any meaningful way?
I mean, you can use ridge to determine whether it helps your prediction, whether they're so correlated that they're harming your prediction. Correlation, if you have the feature matrix, you can very easily compute the sample correlation matrix. You just do basically X transpose times X. You divide by the number of samples. Now you have a matrix that has all the correlation values in it. And so, if those numbers, the numbers off the diagonal are much greater than 0, then that would be an indication you have a lot of correlation. Now, whether that affects you is, in a negative way is a different story, I guess. But you can get the correlation just alone without doing anything more than just that sample correlation computation. Okay.
Does the correlation have to be highly linear as well, or can it be any?
So correlation has a particular definition. It's like the average value of one thing minus its mean times another thing minus its mean. So that's what correlation means in this case. Okay, great questions. Any other ones? Okay, so so this is a summary, but I think I've basically repeated all this stuff already. So let's actually start to dive into the code, because there's sort of a lot to talk about here. Okay, so the first thing to talk about is is how does Lasso show up in scikit-learn? So basically, it looks exactly like the linear regression. So both of them are in this linear model class. The only difference when you instantiate them is you write Lasso instead of linear regression here. Okay, and this makes your Lasso object. Once that's made, you can do things like this. You can select the value of alpha that you want to use with it. It has some default value. I can't remember what it is, but it's in the code, the documentation. And this is how you fit it to your training data. So exactly how you do the linear regression, exactly the same interface. And then when you want to do prediction, you do Lasso prediction, just like the linear regression as well. Okay, so that's how Lasso looks. Okay, now the main difficulty is choosing the regularization weight using k-fold cross-validation. Okay, so at a high level, we could start with this approach. I want to say this is what we're really doing here is we're now, just because it's the easiest thing for me to show you first, I'm going to show you how to do cross-validation with these biased Lasso coefficients. It's not what we want to do, so I'll put a little frowny face here, but it's just the easiest place to start. So just like when we did k-fold cross-validation to select model order, the code is almost identical. We have 2 for loops. Previously, we had model order D, and we made a list of the different Ds we wanted to try. And then we did this double for loop. And for all values of the test fold and the value of D, we made a matrix. And then we basically averaged the rows of that matrix to find what is the average cross-validation RSS, or mean squared error, for each value of D. Now we're doing exactly that, but we're using, instead of D, we're using alpha. We're going to make a grid of alphas. So here's how we make that grid. It's important to make this grid log spaced because we want these alphas to span many orders of magnitude. So here we're doing 10 to the minus 3 to 10 to the power 1. And the number of alphas we're going to use, the more you use, the finer, it's just like a resolution thing. The more you use, the longer it takes, but the more fine-grained analysis you can do. So we're using 100 values here. Other than that, the code looks exactly the same as before. You have an outer loop, which goes over all the different folds in your k-fold object. So here's where we created a 10-fold, k equals 10, k-fold cross-validation object. We're using shuffling. So here's where we're creating our training and test data. In the inner loop, we go over our different alpha values that we're testing. We choose the one we're going to use at that iteration of the loop. We fit according to our training data. We predict our test labels. We then compute the mean squared error, or the sample mean squared error of those test labels. And we store both of these in this MSE matrix. So in the previous unit, I was calling this normalized RSS. I think in hindsight, maybe just calling it sample MSE is the clearest thing. So here, we can replace this with sample MSE if you like. Oops. Or normalized RSS, however you want to call it. Once we go through this for loop, we've collected all these mean squared error values, and we can use them to compute 2 things. First, we can compute we can average over all the k-folds to find the mean squared error for every value of alpha. And we can also compute the standard deviations and divide them by the square root of the number of folds to get the standard errors. And we can then use that for the one standard error rule if we want. Okay. So that's what we've done here. And this, like I said, is exactly like what we did for model order selection, except now we have a grid of alphas instead of a list of D values. Okay, any questions on that? Yes.
So
over here, you have not checked the correlation of the parameters which are being used in training data set.
Right.
How can you, I mean, I don't know if you're counting in data, but how can you say that Lasso is the optimal method to actually do it when you're not checking the
We never know the optimal method. We always bring to a data set maybe a library of methods, and we try many different ones. And I mean, this is real machine learning. You never know, right? You've learned about maybe many methods in your courses, or you've read about them online. Now you go about trying them, and now you need a way of comparing them all. So maybe for this purpose, you hold out some fraction of the data that you don't use to train any methods, but you use it to choose among the methods. Yeah. So here, all we're doing is we're saying we are going to use Lasso. So I'm just trying to show you how to use Lasso. We're not doing Ridge. We're just doing Lasso and Lasso alone. And really, the problem we're trying to solve is how to choose alpha well for Lasso. Okay. Good. Okay. So this is a lot of work to type all this out. So it turns out, not surprisingly, the scikit-learn has more or less 3-line solution to all of that. And it's with this super useful command, which is grid search CV. This is one of the commands you'll use most. So for grid search CV, let me show you the things it wants. For grid search CV, you have to tell it what is your estimator. So we set up this Lasso object. So now it knows we're doing Lasso. You have to tell it which parameter are you trying to optimize. So we're trying to optimize alpha. So this is how we set up the parameter grid. So the thing we're trying to optimize, which is alpha, has to be a known thing for this estimator. So if you look up the literature or the documentation for Lasso, you'll see that the alpha parameter is one of the things in Lasso that can be tuned. So we can tell grid search CV, okay, I want you to try tuning the alpha, and here is the range of values I want you to use. So alphas is this thing we created over here. So that's our grid. So it's going to do cross-validation to investigate all the different choices of alpha in this grid. Yes?
Could that take multiple models?
Yes, it can. If you give it a pair of things, it will look at all combinations of that pair. If you give it 3 things, it will look at a data cube of all those possibilities. So yeah, it can use as many as you want. Of course, the time it takes starts to increase exponentially as you add more and more.
How would it compile it? Would it be like a tensor multiple layers?
Yes, it gives you an n-dimensional array.
Okay.
Yeah, exactly. Okay, then you tell it how you want to do the cross-validation. So we're using k-fold cross-validation. We created this k-fold object up here already, so this is exactly what we're giving it. So this knows to do 10-fold cross-validation using shuffling. You could instead do a leave one out. There's a scikit-learn model selection, leave one out, and then that would do leave one out. Or you could do repeated k-fold. There's many options you can use. Whichever one you want to use, you create that object and you stick it in here. The last thing you have to tell it is what score are you going to be using. Just like last time, we're using negative mean squared error. So now that this is all set up, you give it your training data and you run fit, and now you sit back and you wait until it goes through all those different alphas, and for every one and for every fold, it has to do that Lasso optimization. So this could take a little bit of time depending on how big your data set is, how many alphas you're testing and all that. But eventually it's done, and it has all those results stored in it. And here we're asking it to report all the cross-validation results. We're asking it to do a mean over all the folds. And it's going to give us the means. And here we're saying do a standard deviation over all those folds. And it's going to give us the standard deviation. The standard deviation for us, we know that's useful because we can divide it by the square root and the number of folds to get our standard error. Except there's a little bit of a complication here, is that when we talked about it back here in Unit 3, we said that when we compute the standard error, we want for the standard deviation to use the unbiased version. Unfortunately, Grid Search CV does the biased version and gives you no choice. So it has 1 over k there. But actually, we can make up for this. Because if you look at what's happening, this thing, or let's say square root of this thing, is going to be divided by square root of k minus 1, and then it's going to be divided by square root of k, right? So if this is implementing the square root of k here, we can change this to the square root of k minus 1 and then get the same result. And so that is what we are doing over here. When instead of dividing by the square root of the number of folds, we're using number of folds minus 1 to compensate for the fact that this is the biased standard deviation. Is that clear? So it's a little trick. Maybe I'll put a little arrow here. Oops. I want this. Okay. Since biased. Okay. So that sort of describes how you would set up Lasso if what you want to do is solve the Lasso problem, use those Lasso coefficients, and then see how well they work, these biased Lasso coefficients, see how well they work for predicting your test targets. Okay. Any questions on that? Okay, so by the way, these two approaches should give you, to machine accuracy, the same numbers. Exactly. This is just a much more convenient way of doing this. So from now on in the course, we'll only do this. We'll never do it the manual way. That's just to explain what's happening. Okay. So what we said is, what's naive about the approach on the previous page and on this page is we're choosing alpha to minimize this RSS bar, or maybe we can say sample MSE. But we're using the biased Lasso coefficients, so that's something we don't like. So we might say, okay, well, maybe as a Band-Aid, what we'll do is once we know the alpha that this technique gives us here, the one that minimizes sample MSE, let's come back to Lasso. Put that found value of alpha into our Lasso estimator, and then fit with the entire training data, right? So because when we did cross-validation, we were never using the whole training data. Now we're using the whole training data. And now let's look at the coefficients that come out. So when you look at them, the intercept is 0, but we expect that. That's the beta naught, because we said intercept should be 0 because we standardized our data. But basically, this is the only one that it's setting to 0. So it's selected 7 out of the 8 coefficients. And when you look at the cross-validation mean squared error given by these coefficients, it's relatively poor. It's a little bit better than using all 8 of them, which is what we did with standard least squares, but it's not that much better. So, yeah, so basically, another thing we can do is we can just say,
Question?
oh yeah, question.
MSE here includes the penalty term.
No.
No.
Mean squared error is, let's look at how mean squared error. Mean squared error is this. It's just the difference between the predicted and true targets squared mean. So it's what we called normalized RSS in the previous unit. Or we could call it sample mean squared error if we want to. But it does not have the L1 penalty term. That's just part of Lasso. Okay, so we said we don't like the fact that these coefficients are biased. These are shrunk towards the origin. So let's say we know we're going to avoid estimating LCP. So let's just have least squares re-estimate all the other values. So that's what we're going to do. Going to isolate the features, the 7 of the 8, and use them for least squares-based linear regression. Okay, so this is how we can do that. You look at the absolute value of the Lasso coefficients, and And then when you compare these numbers to 0, this gives you a logical vector of like true and false, or 1 and 0, that will have 1s wherever the coefficient is non-zero, and a 0 whenever the coefficient equals 0. Does that make sense? So we have a logical vector now. And what we want to get out of this logical vector is a set of indices. So we can do that with this numpy where command. That says which indices in this logical vector are non-zero. So finally, this gives us the subset we want. We'll call it subset. And now when we in order to use our data restricted to that subset, it's easy. You take your X training matrix, and this says use all the rows and only this subset of columns. So NumPy is smart like that. So this new data set here does not contain this LCP value. It's just omitted. And now we can use cross-val score, which is that shortcut we learned recently. We give it our linear regression object. We give it our now reduced training data set, training features, training targets. We use repeated k-fold like before, negative mean squared error scoring. When we run this, it computes cross-validation scores for this least squares linear regression. And now we can look at the mean of the scores. We negate it to get rid of the negative. And we finally get the mean squared error, the cross-validation mean squared error of what we're calling here Lasso LS. And this one, as you can see, is a lot better than this. This is because this one does not suffer from these biased coefficients. What we learned about linear regression is that at least when we don't have under modeling, the coefficients are unbiased, right? We learned that at the end of the last unit. So that's why we're doing this. We have unbiased coefficients. So that's good. This was an improvement. However, it's still not right, because the alpha that we used at the very beginning, in order to compute this alpha, we were actually looking at those biased Lasso coefficients. And we said we don't want to use them for anything. So this alpha is itself corrupted. So this is why we're going to call this a naive method. It's naive because this alpha was computed based on the previous page, which was computing mean squared error based on all the Lasso coefficients. We don't like that. So there's going to be two approaches that I'll describe now to get around this. The thing that we really care about, I'm going to call Lasso plus LS. So in Lasso plus LS, what you do is you use Lasso just to figure out which coefficients to use, least squares to estimate the values of those coefficients in an unbiased way. So in other words, we want to tune alpha to minimize the RSS, or mean squared error, of Lasso selected least squares coefficients. So we can do this with a for loop. It's not too complicated. So here's how we set up our alpha's vector. So we're going to use a log space from -2 to this number. I can't remember why. I think I just chose that to make the plot look nice. 100 values. We're initializing some vectors of mean squared error and standard error. And so then we have a for loop where we just loop over the alphas. For the alpha that we're currently using, we load that into Lasso, and then we do fit on our training data. And then as soon as we get Lasso fit, we can look at the Lasso coefficients, look at their absolute value, and now we're going to do this threshold. I can't remember why I'm using 1e minus 5. I think if you use 0 here, it should also work. We're getting the subset of non-zeros, but now this is a logical array. And now to turn that logical array into an array of feature indices, we use the numpy where, exactly like the last example. And here again, we're extracting the features we want. Now we're doing cross-val score with a linear regression. But the key point is that this whole thing is inside a loop. So for every alpha, we compute a different subset, fit least squares differently, and then compute the mean squared error from cross-validation. Both the average mean squared error as well across the folds, as well as the standard error. Okay, and this is what you get. you get a plot that looks like this. This is the mean across the folds of the mean squared error versus alpha. And you can see that it has sort of a stair-step form. This is because there's many alphas in here. But for all those different alphas, Lasso was selecting the same subset of coefficients, which means that the least squared estimate will be identical for all those values. And at some point, alpha crosses into a new regime where Lasso is now leaving one coefficient out. And then, for a while, for all those alphas, you get the same subset of coefficients, the same least squares, and so on. So that's why you get this stepped approach. And so when we do, the simplest thing we can do is just say, minimize the mean squared error. Which alpha minimizes this? And so actually any alpha in this range would give us the same mean squared error according to this method, right? So we could use any of those. What I'm showing in the orange line is actually the top of the error bar, so to speak. I could have plotted error bars here, but it would have looked really ugly because there's 100 points. So it would have been like all error bar. So instead of that, I'm just showing you the top of the error bar in orange. So if we wanted to do one standard error rule, we could do that. In that case, you would set your target. You would look at the top of the error bar at the minimum value, set your target as that, and then find the simplest model which falls under that target. And as you can see, that would be this model here. That's the alpha you would choose if you wanted to do that. In the code, I'm not doing that. I'm just using this simpler approach. And actually, the cross-validation MSE is the best we've seen so far. It's better than the previous method. It's the best we've seen. So this is one way to do it. Any questions on this way? Okay, so a few years ago, I had a really smart student, and he said, I actually think there's something that's troubling about what you're doing here, because you're doing cross-validation here. And so when you do cross-validation, remember, you're supposed to use only the training folds to design the model, and you're not supposed to use the held-out test fold for any model design stuff. So do you see where this is going kind of wrong, where we're cheating? So that test fold that we're holding out here has been used to design what? The subset. Yeah, right? So alpha is just on a grid, but like for each alpha, we're designing the subset based on the whole training data. So we're not really doing the cross-validation correctly. We're using the whole training data to choose the subset, and then we're doing cross-validation just of the least squares part. So there is a different way to do it, which is a little bit more pure, and it requires to use some slightly more advanced tools from scikit-learn, but they're good to know about. It's what's called this pipeline method. So ideally, what we would do is we would just use grid search CV. That's the main thing we want to use. We want to use grid search CV. We want to plug in one single estimator that does these three things: lasso, then feature selection, then least squares. We want to cram those all into one estimator and plug that into grid search CV. So the way you do that in scikit-learn is what's called the pipeline. You give it basically a list of different operations, and it basically treats them as a whole. So here's how we set up the pipeline. The pipeline, it ends up needing to use 2 blocks, not 3. We can give them whatever names we want. So I'm going to call the first one lasso, and I'm going to call the second one least squares. And when you look inside these, you can see what's happening. So on the inside of this lasso, we have the linear model.lasso. So that's the main method we're using. For that middle step, which selects the coefficients that are non-zero, scikit-learn has a special thing called select from model. So that is now wrapped around lasso. And what comes out of that is going to be a subset of indices. Then that is going to be put through this standard linear regression, which does the least squares part for us. And we're calling this whole thing pipe. That's our new method. So this thing we can plug directly into grid search CV, which is really cool. Now, when we declare the parameters, that gets a little bit more complicated because there could be parameters inside least squares, there could be parameters inside Lasso, and so on. So we have to tell it where to find the parameters. So here's how we do it. We say, look inside the Lasso part of the pipeline, and then there's this double underbar. And then we say, look inside the estimator part of Lasso, because there's really two parts. There's the select from model part, and then there's the estimator part. So we say, go inside the estimator part, and there you'll find alpha. That's what you're going to tune. And here is the grid that you're going to tune it over. If you're curious, like where did this syntax come from, just do pipe get parameters dot keys, and that will print out the options, the tuning options for you, so you don't have to like guess to come up with this. Okay, so once that's set, now you can use your pipe exactly as you usually do in grid search CV. You do your fit method, you sit back, you wait a while, and eventually it churns through all the combinations. And here's the plot it gets. It looks quite a bit different than the previous one. Now we see that for each one of our alpha values, things are a little bit different. And overall, we could use this. This is the model that gives us the lowest cross-validation MSE is this particular alpha. Or we could use one standard error rule, which says look at the error bar to figure out the target. Now look at the simplest model that sits under that target, and the simplest model is here. That's the value, the blue. And now, another thing I forgot to mention before, since we're dealing with Lasso, simpler is larger, right? Because unlike with model orders, polynomial model order D, whereas as D gets bigger, it gets more complex. Now, as alpha gets bigger, you're turning off more and more coefficients, so now it's getting simpler. So simpler is to the right, so that's why we're looking for the place to the right where this blue curve sits under the target. Okay. So that's it. And it turns out, with this one standard error rule, the value you get is identical to this other method here. So they're both giving you exactly the same set of coefficients, same everything. So that's good news. And it's pretty good. So I'll show you. Okay, here's the final. So in the demo, in addition to these methods, the demo also looks at all these other methods we talked about. So let's just go through them. So first of all, exhaustive least squares. Remember, that is the optimal method. When you do that with this prostate data set, you get 0.388072. That's the best you can do. If you do plain least squares, no feature selection at all, that's the first thing we did. That's worse, 0.403. Now, if you do ridge regression, that's also really bad because we know that doesn't do model order selection. It deals with correlation, so that's not helping us here. This first lasso here, this is the bias lasso. This is also really bad. This second one is where we chose alpha in a biased way, but then we selected coefficients and ran least squares. We're going to call that de-biased. That is a little bit better, but still not very good. Then we have these two methods for Lasso plus least squares. They give things that are not quite as good as optimal, but very close. And then we also, remember we talked about recursive feature elimination. That's the backward selection. So when you do that also basically ranks the features, and then you can use that ranking in least squares in an unbiased way. That gives you identically the same performance as these Lasso plus LS methods, so they're all equal. And finally, recursive, or this RFE-MI, this is the mutual information one. That one is terrible. Essentially, this is selecting all the features just like least squares and it's not doing any model selection at all. Okay, so this gives you just one picture. It's not going to be like this in every data set, but in this data set, that's how it fell out. And this is, I would say, kind of typical. Okay, so are there any details here that we want to get back to or anything to talk about? Okay, yes.
While you were doing feature selection, you also wanted to like change the model order of certain features. Can you cascade that with Python?
Well, feature selection is kind of controlling the model order because it's telling you which features to use. And then that, like if you just count them, you could say that that's the model order. Like if I'm using 3 features out of 10, I would have a model order of 3. So I'm not sure if you're asking about something different.
Possibly, like for one of the features, instead of using that feature, use that square.
Oh, if you want to do, so I would say for that, what you would want to do is you can augment your original data set with those extra polynomial features, and now you just have you have more features. And now you can use any of these techniques as you like. And if they work, they will learn whether or not to use the squared feature. If it's not useful, hopefully they'll just say don't use it. Yeah, so that's how you would approach that problem. Okay, so yeah, Lab 4 plays with this stuff, and it plays also with Ridge, so you can see both at work. If you wanted to play with Lab 4, let me just explain one detail, which I'm skipping to the end here. But the lab uses vector-valued targets. What I mean by that is until now, our targets have just been single scalar numbers, right? But in this lab, you're actually predicting a vector of targets. So we can think of it as vector y instead of scalar y. The way we handle this is rather than having a single beta vector, we actually have a bunch of different beta vectors. So the first beta vector is used to predict the first target, the second one, the second target, and so on. And so now we have a beta matrix. Well, I'll call it B because there is no such thing as a capital beta. But this new B matrix has K columns if we have K targets we're predicting. Okay, so that's the difference. So we basically have a coefficient matrix instead of a coefficient vector. And our model, but other than that, our model looks the same. We have a Y matrix, a beta matrix, call it B. A is the same as before. The nice thing about scikit-learn is it doesn't care. It's seamless. If you use vector-wise, it will make a matrix of betas, and it takes care of everything, no problem. So that's easy. Notationally, I just want to point out a couple things. So when you do ridge regression, in this case, the idea is the same. You want to penalize the sum of the squares of your coefficients, right? What changes is the notation. So it turns out that when you have a matrix and you want to measure the sum square coefficients of the matrix, you use what's called the Frobenius norm. If you use the 2 norm of a matrix, it has a totally different interpretation. It's actually the maximum singular value of that matrix. It's kind of like what's the biggest gain you can make in a vector if you multiply that the vector by that matrix? How much can it stretch a vector? That's what the 2 norm of a matrix is like. That's not what we want to use. We want to use the sum of the squared values, which is the Frobenius norm. Okay. So ridge just has a notational change. Lasso ends up not having any change because the 1 norm of a matrix is just the sum of the absolute value coefficients in that matrix. So that one is the same as before, but ridge has a notational change. Okay, so that's really all I wanted to say at the end, just in case you want to start playing with the lab. What we're going to do next week is we're going to get into a little bit more of a theoretical viewpoint on all this. And it's going to be a powerful way of thinking about things that we're going to use for the rest of the term. It's called maximum likelihood, but we'll save that until Monday. Have a great weekend.